Hello, and welcome to this review of our Math 222 final exam. We're going to go over the study guide that you can find in Canvas. And we're going to go over one of each type of problem so that you're ready for the exam. So first of all, there's a couple of tips to remember in general. Make sure you answer all parts of each problem. Pay close attention to when they say things like explain or how do you know or something like that, okay? Make sure that you do answer all parts. When writing a word problem, make sure you're actually writing a problem that doesn't tell the students things like find the LCM or find the GCF. In other words, you're writing a situational problem. Joe wants to buy hot dogs that come 6 in a pack and buns come 8 in a pack. What's the minimum each that they can buy? Something like that. You're not saying find the LCM or find the GCF, okay? You're writing an actual problem that students have to solve, not even realizing what they're using, like LCM and GCM. And then good luck. Okay, so let's just go ahead and get into our review. I've already started showing the work on number 7.1 here, but does this double number line show a proportional relationship? How do you know? So there's the two parters here. So when you're looking for a proportional relationship, look across the top, see that it goes up by the same number, 0, 3, 6, 9, 12. If it was 13, right off the bat, no, it should have been 12, that kind of thing. If you look at the bottom, 0, 5, 10, 15, 20, same thing. So yes, this is proportional because the ratios remain the same. And you can also write it as 3 over 5 equals 6 over 10 equals 9 over 15. All of these fractions reduce back to 3 over 5, or 0.6 if you were to divide them out. So that's how I know it's proportional, is because the fractions all reduce to 3 over 5, or the cups of grape go up by 3s and the cups of peach go up by 5s, and it's consistent. However you want to explain it, but those are some of the different ways you can do that. Now, when we talk about strip diagrams, it's been a while, it was in chapter 7. So let's go over an example. The ratio of Joey's trading cards to Heather's trading cards was 9 to 5. The strip diagram below shows this relationship. So if you look, Joey has 9 cards. We put a 1 in each box. And remember, when you're solving a problem, if you're using boxes, that's kind of like an X or a Y. So you want to stay consistent. So in each one of Heather's boxes, we also put a 1. So that's my 9 to 5 ratio. Okay? Now, after Joey gives 6 cards to Heather, they have an equal number of cards. And then we're asked a few questions. Make sure you read very carefully how many trading cards did Heather have. It could have said Joey, so make sure you answer this properly. When they have an equal amount, how many does each person have? In other words, what is the amount that each person has? It would be the same number. To solve this, use the strip diagram below and explain what number goes in each box. So let's go back up to the top here. We have a 9 to 5 ratio, but that's also 18 to 10. If I go up by 9s in the top and 5 in the bottom, that would also be 27 fifteenths. And I can keep going, 36 20ths and so on. But let's see, we don't know how far I have to go yet. But all of these are possibilities and then some, right? There's an infinite number that it could be. So one thing I know is after Joey gives 6 of his to Heather, they have the same amount. So look for one of these that if I take 6 away from Joey and give it to Heather, I get the same amount. So if Joey gives away 6, he's got 3, Heather gets them, she's got 11. Nope, that's not it. If Joey gives 6 of his 18, that's 12, she's got 16 now. Nope, that's not it. If Joey gives 6 of his 27, he's got 21. Heather gets his 6, and now she's got 21. There we go. So we actually know part B right now. Part B is 21. When Joey gives away 6 of his 27 to Heather, she now has 21, and so does he. And then if you look at part A, how many trading cards did Heather have? We're using this fraction. Heather had 15 at first. And again, could have asked how many did Joey have? He would have had 27. And then to solve this, we've kind of done that already, but let's go ahead and do the strip diagram below. What number would go in each box? So remember, we want Joey to have 27 and Heather to have 15 at this point. What number would have to go in each one of these boxes to get 27? And remember, the same number goes in this box to get 15. And what you do is you actually are going to divide. 27 divided by 9 is 3. 15 divided by 5 boxes is 3. So I need to put a 3 in each one of these question marks to get 27 for Joey and 15 for Heather. Okay. Explain what the multiples and factors are of 45 and when do they end? So let's look at the multiples. The multiples of 45, the way the book defines it is if you start with 45 times 1, you get 45. If you do 45 times 2, you get 90. 45 times 3, you get 135, and so on. These never end. Okay, multiples can go on forever. So to explain what a multiple is, it's when I multiply a counting number by the number infinitely. Okay. You can also say they're the numbers that the given number goes into. So 45 goes into 45, 45 goes into 90, 45 goes into 135. And when I say goes into, I mean with no remainders, okay? Now for factors, the factors are the numbers that I could multiply to get 45. So I could do 1 times 45, and normally we just write these in a list. So let me write it the way that when you work it out, you probably do this. I can do 1 times 45. I can do 3 times 15. I can do 5 times 9. Now it's going to flip backwards and go 9 times 5 and 15 times 3 and 1 times 45. So when you list them, you can write it that way. I wouldn't have any problem with that. But you can also say 1, 3, 5, 9, 15, 45, because you're just listing them in order, least to greatest. Either way is fine. So when do they end? These end when I'm done figuring out numbers that multiply to 45. The main part of this question of when they end would be if I was talking about multiples, because multiples never end, but I do have a finite number of factors of 45. These are all the whole numbers that I can multiply and get 45. There's nothing else. And I know when I start going backwards here, right? 5 times 9, now the next one is 9 times 5, 15 times 3, and so it goes backwards. Okay. 8.2, suppose you are adding even numbers together. Will the answer always be even? How do you know? What about adding two odd numbers? What about one of each and so forth? So this all goes back to the part where we were talking about an even number being 2 times n, where n is a counting number, okay? And an odd number would then be 2 times n plus 1 or 2 times n minus 1. And you can think of on a number line, they alternate. And you can use a number line to do this too if you want. The neat thing with math is you can explain this a bunch of different ways. I'm going to show you a couple here. So let's look at all the different situations. If I take two even numbers and add them together, I would get 2n plus 2n is 4n. There's no 1 or minus 1. I'm sorry, there's no plus 1 or minus 1 if I'm adding two evens. So I don't have that left over or to take away one. So I still have an even number. Because if I do 2n plus 2n, I get 4n, right? So two evens added together gives me 4n, which is still an even. What about if I do, what's the next part here? Basically, I want you to know all of this. So I'm just showing every part that it could be. Will the answer always be even? Yes, because there's nothing left over. A lot of students say if I divide them into equal groups, there's no leftover. That's okay too. Again, if you used a number line and you started on an even and you moved an even number to the left or right, you'd end up on an even. You can do that. So there's a lot of ways to explain these things. What if I add two odd numbers together? So I would have like a 2n plus 1, and let's say I'm adding another odd 2n plus 1 or minus 1. 2n and 2n is 4n. 1 and 1 make 2. That 2 becomes another n, basically. I have another pair, so it's still even. Or this is kind of a neat way to do it too. Since an odd number is 2n plus 1 or 2n minus 1, if I do that way, the 1 and minus 1 cancel out. And I get 4n again, which is just like two evens. And then what about an even plus an odd? You could probably see what's going to happen. I'm going to get 4n again. But now I have that strange plus 1 part hanging around. So that's an odd again. It all has to do with that remainder, that 1. If it goes away, again, if it became 2, when I had two odds, 1 and 1, and I had both positive, that became another even because I had another group of 2. So you'll want to know kind of all of these things and how to explain it. Totally up to you, but make sure the how do you know the explain part is taken care of. Mathematically, this is awesome, but I totally understand if you want to say, let's say I have 4 and 8, I add those together, I get 12. 12 is an even. Remember, that's not going to prove that it always happens, but then you could say, since those two even numbers have no remainder parts left over, I'll always get an even. I'm going to leave that up to you how you explain it, but be very careful if you use like one example. That's not saying that it's always going to happen. So make sure you know how to explain that. Okay, explain how to solve the following proportion by reasoning about numbers and operations and expressions, not by using standard techniques and algorithms. In other words, don't just multiply everything out and then cross multiply and divide and solve for x. That's great, but that's not reasoning about the numbers. When we say reasoning, we want you to actually be able to say, all right, let me look at this. I have a 21 on the left. This is my main dividing thing here, dividing my equation up here, right? Here I have a 21 and a 15, and over here I have a 21 and a 15, which really is just 1, or 1 over 1. Well, I'm getting ahead of myself. Let me back up here. I don't want to explain it that way because they don't cancel out. Let me circle them instead. I don't want to make it look like I'm canceling things out here. But this fraction over here is the same as this fraction over here, okay? I don't want to cancel things out with marks. That leaves me just looking over here, okay? I do know that these are the same thing. What would this have to be so that I could get 1 over here? 3 times something over 24, because I want to take this circle, multiply it by something, and still get this circle. Does that make sense? I hope. I want to take this 21/15, multiply it by something, and still get 21/15. So I must be multiplying by 1. So really, this 3x over 24 needs to come out somehow to just be 1, because I'm multiplying 21/15 by it and still get 21/15. So if I look at this, I'm not even looking at the 21/15 now. I'm not cross multiply. All I want to know, what would I have to put in for x so that 3 times that would give me 24, so they would cancel out and give me 1. Well, if x was 8, 3 times 8 is 24. 24 over 24 is 1. Okay, that's how we reason about numbers instead of actually doing, okay, 21 times 3 is 63x over 15 times 24 is whatever. We're not doing all that. We want to be able to look in our head and immediately know that these are the same thing. So I need to multiply 1 times this. What do I need to get 1 here? If x is 8, 24 over 24 is 1. Okay, a circle is partitioned into 6 equal parts so as to create 6 identical angles, each with a vertex at the center of the circle as shown. If each of the 6 angles measure x degrees, what's the value of 3x? So first we've got to find x. Well, there are 360 degrees in a circle. And I have 1, 2, 3, 4, 5, 6 pieces. They already told me that. But if I divide by 6, that gets me 60 degrees per piece, per slice, per wedge. And then they're simply asking what is 3x. So I actually found the value of x here, right? By doing 360 divided by 6 is 60. So 3 times 60 is 180 degrees. That's all. Once I find each one, look at what they're looking for, 3 times x, 3 times 60 is 180. So you do need to know that there are 360 degrees in a circle. Okay, know how distinct circles meet. This is the key. Okay, distinct. Distinct means different. They're different circles. I'll explain that in a second. So here's one circle, here's another circle. They're definitely different circles, right? These circles are not touching. They're not meeting at all. So one answer is they do not touch. Okay, two distinct circles may not meet at all. They could meet in one point. Let's just say that's one point there, okay? Or they could overlap like that. That's a pretty good drawing of a point there. So they could not meet at all. They could meet in one point like that, touching, or they can overlap and meet in 2 points. Again, these are distinct circles, so they're different circles. If I were to just say, how could 2 circles meet? Well, if they happen to be the same circle, they could meet like that. They could completely overlap and be the same circle, every single point. But the word distinct means that is taken out, okay? So this is what I want you to know. All right. Are squares always rectangles? Always, always, always. Be careful with the word always. And be careful saying this can't be this, because as soon as you say this can't be this, if there is a situation where it could, you're not being mathematically completely correct. So you want to know the hierarchy of all of these shapes, okay? So are squares, sorry, there should be an S there. Are squares always rectangles? Okay, the definition of a rectangle from our book is a four-sided shape that has 90-degree angles. And we also defined it as saying opposite sides are congruent and parallel. So when we think of a rectangle, we typically think of this one here. When we think of a square, we think of one of these two, right? Down here. Are squares always rectangles? In a word, yes, they are, because they meet the same requirements. There are 90-degree angles inside. They have opposite sides that are parallel and congruent. It just happens that all 4 sides are the same. Are rectangles always squares? Absolutely not, because here's one in the top right here. That is not a square, right? You would give me an example. You could throw in numbers if you want, or you could say it could be taller than it is wide, right? Something like that. Are parallelograms always rectangles? Well, parallelogram could be slanted, to use a non-mathematical term there. A parallelogram could have a look like this. Sorry, just sketching it really fast. It's where you take a rectangle and you kind of slant it. Very bad drawing, but definitely that is not a rectangle. But a rectangle is a parallelogram because it still meets the definitions. It just happens to have 90-degree angles. So you want to understand all of that hierarchy of rectangles, parallelograms, and so forth. Okay, 13.1, explain the difference between a triangle and triangular prism. So mainly you're going to want to look at section 13.1 in the practice problems for this. Basically, I'm looking for 2D and 3D differences. Okay. Triangle is a flat three-sided figure. Triangular prism is three-dimensional, and you'll describe it as such. And that's honestly what we're looking for. Three-dimensional figures also have volume, where 2Ds don't. They have surface area, 2D figures don't. So you'll want to be able to say things like that about the difference between two and three-dimensional figures. So find the total surface area of the figure below by finding the area of each rectangle and adding them together. So this is, let's say this is a Kleenex box or something, you cut it and you unfold it. It's called a net. Find the total surface area. Surface area is simply finding the area of each side and then adding them up. So 3 times 4 is 12. Which one is this? This is 5 times 4, right? So that's 20. And I'm not writing feet in here or square feet, but that's what we're in here. That's what our units are. 5 times 3 is 15. 5 times 4 is 20. And 5 times 3 is 15. Notice I have 2 12s, 2 15s, and 2 20s. That makes sense because I have 3 different sides in this case. Some of them could have been the same, but I have 3 pairs of sides. So you can simply add all these numbers up, or you can add the different ones and double that. So I could do 12 plus 15 times, or sorry, 12 plus 15 is 27. So that makes 47. 47 squared is 94. So 94 square feet. Now here is where you do want to put in your units and be picky. 94 square feet. And again, you can add it up, 12 plus 12 plus 20 plus 20 plus 15 plus 15, however you want to do it. Just making sure, 24, 44. I do that wrong in my head. 47. Let me just double check. $94. Okay, sorry about that. I was just making sure. Never hurts to double check your figures. And also what I was trying to do in my head there, just to see if I had done it right, 12 plus 15 plus 20 times 2. Okay, 94. All right, moving on. 13.3. I will give you the formula for the volume of a sphere. Be very careful. If I give you the diameter, you would have to divide it by 2 to get the radius. In this particular case, I give you the radius. Now, I'm not going to be picky on how you do this, but make sure you know how to put it in your calculator. I'm just going to do this the simplest way possible here. If the radius is 6, I have 4/3 times pi times the radius to the 3rd power. Literally, 4/3 is 4 divided by 3. All right, times pi. You can hit the pi button. Times 6 cubed. Now, I'm lazy. I don't want to look for the cubed button and all of that stuff. So I'm just going to go times 6 times 6 times 6. Okay, or 6 to the 3rd power. I guess it's right there on my calculator. 904.778684. Okay, it says to round to the nearest hundredth. Just to be picky, 904.7. I look at the next digit, which is the hundredths column, is another 7. And the digit after that's an 8, so it's going to go up. So 904.78. 904.78 cubic inches. Now, I'm not going to be picky about the rounding. It's somewhere between 904 and 905. Okay. If you use the pi button, you'll get something different. If you use 3.14, you'll get something different. And as a math teacher, I honestly prefer 4/3 times 6 cubed 288 pi. would be fine too, to just write 288 and then the pi symbol. Because again, if I multiply this by pi, there's my 904 point something. So you could have just left it as 288 pi. But the directions do, in this case, say to round to the nearest hundredth, so I did that. But I won't be too picky. Make sure you just know how to plug these in and get the answer. Okay, this one takes some work, so I've already set it up here, but I'm going to explain it. On graph paper, draw the x and y axes and plot the following points, label them E, F, G, and H. Plot the locations of these points after they have been translated 2 units down and 5 units right. What would the new coordinates be? So we just went over this a couple lessons ago. There's a mathematical way to do it without making a graph. But if you want to use graphs, you can sketch one on scrap paper and do this. That's perfectly fine. I don't need to see the graph. I just want to see how you're coming up with the answer here. But you can do it without graphing. And I've never really done it this way before, but I did this just yesterday. When I'm looking at an ordered pair like 3, 1, 3 is x, 1 is y. Remember which one is which. So I thought I'd make a little table. So across the top, I put x, y. And what am I doing to x? Plot the locations after they've been translated 2 down, that's the y part, 5 units right, that's the x part. I purposely wrote that different. Make sure you read very carefully which one comes first in the example. So 5 units right means x plus 5. I start on the x-axis, or wherever that point is, the x coordinate goes 5 to the right, so plus 5. Y being 1, in this case, I'm going to go 2 down, so that's y minus 2. So what I did was 3, 1. I wrote 3, 1. Well, x plus 5 would be 3 plus 5. That's 8. Y minus 2 would be 1 minus 2. That's negative 1. So there's my first new ordered pair, 8, negative 1. If you want to do it in a table like this and just leave it like this when you're done, I didn't do all the points, that would be fine too, okay? I'm okay with that. But again, this simply is 8, negative 1. And I know in Canvas, it's not easy to draw this kind of table out and so forth. But again, you could do this on your scrap paper and then write 8, negative 1. It's fine. And then the next point was negative 4, 2, negative 4, 2. Now, what I like about this is it is just substitution now. So negative 4 plus 5 is 1. 2 minus 2 for the y is 0. So that is 0.10. And so on. Now, you don't have to use a table. You could just do the math in your head or use a calculator to be careful with your negatives. But that's all you do. It's just adding or subtracting. Remember when we're talking the x coordinate, it's left or right. If I go left, that's subtraction. If I go right, that's addition. And if I'm going up or down, that's y. That's up would be positive and down would be negative. Okay. You're going to be asked to define lines of symmetry. So here's an example of a rectangle. I could fold a rectangle in half this way or this way. Quick approximation there. But I can't do it any other way, right? If I put this line across the diagonal, I think you can see in this particular case, this piece comes up here, this comes down here at an angle. The diagonal of a rectangle is not a line of symmetry. Okay, try it with a 8.5 by 11 piece of paper. It won't line up. So in this particular case, now I'm not going to ask you to draw them because it's a little hard to do again in Canvas. So I will ask you to describe them. Be careful not to leave any out. So when you're describing, let's say I gave you a rectangle, you could say it has a line straight through from the left to the right side and the top to the bottom. So there are 2 of them. Or you could say diagonals don't work. If you don't say the parts that don't work, that's okay, but it does show you really understand if you do say something like, there's no diagonal because it wouldn't line up. But again, the specific question is to describe them, one through the top to the bottom and one from the left to the right, that's fine. But make sure you actually say the number, two of them as well. This is a problem that we just changed because we got a little deep into side, angle, side, and you don't really need to know a lot of that for what you're studying. So we've changed this question, and I think this is a lot better type of question, okay? So given the figure below, sides AD and AB are the same length. So you can see I actually made the mark here. AD and AB are the same length. And the measure of the angle formed at A for both is the same. So I put this little mark here. This angle and this angle are the same. So hopefully you can see that there are actually two triangles here, right? There's ADC and ABC. Are the two triangles congruent? How do you know? Do I have enough information here to say, or, I might not even have enough information to say that. Are they congruent? How do you know? There are three possibilities. Yes, they're congruent. No, they're not congruent, or there's not enough information. Well, if I look here, they both have this same side AC. Side AC belongs to the triangle ADC, and side AC belongs to ABC. So really, I actually know that this side is congruent to itself because it's in both triangles. So if I look, I actually have this side here, AD, and then the angle up here at A, and then AC. I have the same thing here. So this is side, angle, side, which is a legitimate way to prove triangles are congruent. Okay? There's also side, side, side. You're going to want to review the ones that we talked about and make sure that you only use those proofs. There's side, 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 etc. But look at the problem and see which one applies. Okay. Moving on. 14.5. A 36-inch by 24-inch poster will be scaled down to fit in a picture frame. So I've already got the poster. So here's my picture frame. On the frame, the short side will be 6 inches long. I almost drew a square there. Let me make this more like a... Let me make sure I do a rectangle because it's not. There we go. So the short side, on here, the short side was the 24, right? Because 36 is bigger than 24. I could have labeled it the other way. It doesn't matter. Excuse me. But I just want to be consistent on the model here. So on the frame, the short side was at the top. So this is on the top. What will the long side be? So what I don't know is this one. So there are a lot of ways to do this. There are a lot of ways to do this. You can get official, set up fractions, do internal factors, external factors, set up equations. There's a lot. I think the most common way to do something like this is to look immediately and say 6 times 4 is 24. So this short side is 1/4 the size of the original. So 36 divided by 4 is 9. And I'm totally okay with kind of doing it that way. Now, to be picky, you could set up fractions, right? 24 inches in the top, 36 in the bottom. So what I'm doing is I'm setting this top to its side. We know it has to be proportional to the top and the side of the other one. So the 24 is in the top of the fraction there. So the 6 is going to go in the top here. And I have some unknown here. even when you set this up, there's still a number of ways you can go. You can cross multiply and divide. 36 times 6 divided by 24, you'll get 9. Or you could do what we already did here without writing it out. 6 goes into 24 4 times. 36 divided by 4 is 9, and that's how I get my 9. You can also say 24 is to 6 as 36 is to x. And cross multiply and divide and get 9. So it's all up to you how you want to set these up as long as you stay consistent. Okay. There's even another way. 24 times 1.5 gets me 36. 6 times 1.5 gets me 9. Okay. So however you want to do these, that's what the beauty of this type of math is. There's a lot of ways to figure that out. Kind of leads us back into our scale factors. So let's look at the 14.7. You're given a square cubic container measuring 4 inches on each side. What happens to the surface area and volume if each side is doubled to 8? Why? Be specific. And then there's a second problem, so I'll skip that one for a second here. So let's look. Here's my 4x4, and they're saying I double it to 8x8. What happens to the surface area and volume of each? And again, it's in 3D. I don't have it drawn as 3D, but it does say cubic here. Okay, go back to this page in the book in 14.7, and you'll remember that scale factors k, k squared, and k cubed. So if it's 4 inches here, in my third dimension as well, and it moves up to 8, right? It doubles to 8. It doubled, but we're actually doubling each side. So it is times 4, 2 to the 2. So what happens to the surface area? It's actually 4 times bigger. The volume is actually 2. Remember, we're doubling it. 4 to 8 is 2. 2 cubed is actually 8 times bigger. Okay. And why? We can look at the formulas for these, but let's do that real fast here, because I don't want to take a shortcut and risk somebody not understanding. So I'm going to add in my other dimension here real quick. Again, forgive my sloppiness, but anyway. So for surface area, let's look at the original surface area. I have a 4x4 face. I have another 4x4 face. And I have another 4x4 face. Okay. I have 3 faces. I actually have 6 total since it's a cube, but I'm kind of doing like the front, the side, and the top. And what I'm going to do is all of that and then double that because I have 2 of them. So 4 times 4 is 16, and 16 and 16. That's 48 times 2. That's 96. Okay. Now I'm going to come in here and use 8s instead of 4s. So I doubled all of my 4s to 8s, right? So now I have 8 times 8, 64, plus another 64, plus another 64 is 192. Now I have to multiply that by 2, and I get 384. Okay, 384. Well, if I divide 384 by 96, see my 4? That 4 is 2 to the 2nd power. So instead of going up by 2, even though I went from 4 to 8, it actually went up by 4, which is 2 squared. So you see surface area goes up by a squared factor because each one of these sides got doubled. Okay. Hopefully drawing it out and actually showing you it will help more than me just trying to tell you to memorize this table. If you know why something works, it's better than trying to just memorize something. But let's look at volume. Volume is so much easier to calculate. Length times width times height. 4 times 4 times 4. Okay. So the original 4 times 4 times 4 is 16 times 4 was 64. And again, I know I'm not writing units down. That is very sloppy of me to do. Um, I'm doing it for the sake of time, but you really should include all your units and inch times inch times inch and so forth. If I change that now to 8 times 8 times 8, I doubled each one. But what's 8 times 8 times 8? I believe it's 512 off the top of my head. Let me see. 8 times 8 times 8. Yes, 512. And if I look at the math here, 512 divided by 64 is 8, which is 2 to the 8th, which proves that it goes up by not 2, but 2 to the 3rd. Okay? I am going to clone this page. I don't want to erase that example. But let's look at the second part of this. The tree stands 36 feet tall. A man next to the tree is 6 feet tall. If the tree shadow measures 12 feet, how long is the man's shadow? So again, this is using proportional reasoning again. And I'm going to draw a little tree here. And this is not drawn to scale because the guy looks as big as the tree. Okay, so the tree stands 36 feet tall. A man next to the tree is 6 feet tall. So right off the, oops, sorry, right off the bat, I'm thinking, oh, he's 1/6 the size of the tree, right? The tree is 6 feet taller than him. So the tree's shadow is 6 feet taller than his shadow. But let's go ahead and fill in the numbers here. If the tree's shadow, so let's say this is the shadow of the tree out here, the tree shadow is 12 feet. Why I'm writing measurements now when I didn't do it in any of the others, I don't know. I'm feeling guilty about not writing any measurements here, any units. Let's write those in. Okay. If the tree shadow measures 12 feet, how tall or how long is the man's shadow? So this is another one of those where you can do this multiple ways. The shadow is 1/3 the size of the height. So if the man is 6 feet tall, his shadow is only 2 feet tall. Or I could set up fractions. Again, I could say the man's height compared to the tree's height has to be the same proportion as the man's shadow, which I don't know, to the tree shadow. And if I cross multiply, I get 72 divided by 36, I get 2 again. Or I could put 36 over 12 is the same as 6 over x and get my 3 or my 2 again. So you can do this in a variety of ways. Okay. Kira asked all of her friends what their favorite sport was. Most of them stated soccer was their favorite. Can Kira assume that most of the girls at her school would also like soccer the most? Why or why not? Well, hopefully you can see that since all she asked was her friends, that's not enough to assume the whole school feels the same way. Okay? We don't know how big the school is, right? We don't know if all of her friends, maybe she's friends with literally everyone in school. Okay? But when you're given a problem like this, make sure you are, again, you're careful about, let's say I asked 10 people in my class. and they all said the same score. If a class has 15 or 20 kids, and that's a pretty good amount of a class, just to make an assumption that, yeah, maybe most people do like that sport. I asked 10 random people out of 20, and all 10 of them said they like soccer. That's pretty good uh, statistics. But in the entire school, that's too small of a sample. And she only asked her friends, right? Most of my friends probably likes the same things I like, or we might not be friends. So you can use that kind of logic to explain that type of a problem. Okay. All right, stem and leaf plots. Given the stem and leaf plot below basketball game scores, what scores were the most common and how do you know? So this is a stem and leaf plot. And remember, they'll give you a little key on a stem and leaf plot, like 4 bar 6 means 46. So you read the stem and then the leaves as a number. 44, 46, 47, 49. There are no 5s. You can't say there's a 50 because there'd have to be a 0 to be a 50. 63, 64, 66, 68, 68, and so on. So what I want to know is what score or scores were the most common. So I have 144, I have 146, I have 147, I have 149. Those now 63, 64, 66. I have two 68s here. 72, 72. I have two 72s here. 75, 76, 81, 84, 88. Nope. So these are, I could say 68 and 72 are the most common because they each appear twice in my stem and leaf plot, and all the other numbers that are there are only there once. Or I have more of them than the others. Okay. All right, find the mean, median, and mode of the data below. This does take a lot of calculations, and I want you to know how to do all 3 of them. Remember that mean is an average. Median is the number in the middle, just like the middle of a freeway. Separates north from south or east from west. And the mode is the one that you have the most of, not the most like the biggest number, but the most of. So when you're given a set of numbers like this, you want to put them in order and kind of cross them off as you go or circle them, but put them in order left to right. Now for the mean, all I have to do is add them all up. So if I add all these up, I get 283. I divide by the number of numbers, and if you count them, I have 13. So the mean is 21.8. I'm going to skip to mode because I'm going to start crossing numbers off here. But I have 3 20s and I have 3 22s. So the mode is 20 and 22 because I have 3 of each of them. You don't add them and divide by 2. You don't do anything like that. You just list them both. Now I might have no mode. If everything was here one time, there's no mode at all because everything's just there once. I could have one mode or I can have multiple modes. You just list them if there's more than one. The median is the one where you kind of cross off the edges, work your way in. And that's why I do it last because I'm scratching out all my stuff here. And then you'll see, oh, I'm not done yet. There's my middle number, 22. Remember, if I had done this and I came up to like these 2 numbers in the middle, right? I crossed off a bunch of things on the sides and I come up with this. This is where for median, you do add them up and divide by 2, okay? If there's 2 numbers in the middle or if there's no standout number in the middle, okay? So we'll need to know those. Billy practiced violin an average of 30 minutes a day for 5 days. How many minutes will he need to play on the 6th day so that he will have practiced an average of 45 minutes in 6 days? Explain your reasoning. Okay, now off the bat, 30 minutes a day for 5 days. I'm going to practice one more day and jump my average all the way up to 45. It's going to be a long day. I can already tell I'm going to have to play a lot of violin here. But let's look at this. If I average 30 minutes a day for 5 days, it could be 31 minutes one day, 29 the next, and 28, and then 32. And as long as it averages up to 30. 1, 2, 3, 4, 5 days. How many total minutes did I practice if I practiced an average of 30 per day for 5 days? That adds up to 150 minutes. Now, I want to practice something, some amount of time on that 6th day. So I'm doing my 150 minutes already, plus something, don't know how many minutes on that 6th day. But when I divide by 6, right, because I want an average after that 6th day. So these 5 numbers, this is instead of writing 30 plus 30 plus 30 plus 30, I've just wrote the 150. But remember, this is 5 days plus a 6th day divided by 6. I want to end up with an average of 45. Okay. How many minutes do I need to practice here that when I divide by 6, I get 45? So this is where I do some cross multiplying and dividing. Okay, so 150 plus n times 1 is still 150 plus n. 6 times 45, ooh, is that 270? Let me see. 6 times 45, 270. Okay, 270. Now I just subtract 150 from both sides and I get n equals, subtract my 150. Was that 120 minutes? Remember, I'm only practicing 30 minutes a day, and now that last day I got to do 120 minutes or 2 hours because I'm trying to get an average of 45. Now, what's also neat to do is to go ahead and check it. So I had 30, 1, 2, 3, 4, 5. I do another 120 minutes divided by 6 gives me my 45 minutes of an average. Okay, a couple more. Given the dot plot below, so here's box and whiskers plot. This is my lowest whisker, it's over the 1. My highest whisker is over the 13. My median is right here at 7. That's that answer. What is the value at the 25th percentile? The 25th percentile is the left edge of the box. So that's 4. The value at the 75th is the right side of the box. Sorry about that. That's 10. And the other thing you want to know is that the box itself represents 50% of the numbers or of the data. 50% of my data in a box and whisker plot is inside that box. And also remember, a box doesn't have to have the median right in the middle, and it doesn't have to look like that. It could be something like this, where this whisker is really far out. The median could be like way down here or way up here. It doesn't have to literally be like in the middle of the box. But 50% of my data is in the box, 25% is above it, 25% is below it. Because the other 25 is here and here, right? 25, 25, 25, 25. Okay. And the last one here, find standard deviation. I'm recording this before we actually do this lesson, but here's how we're going to talk about it when we do this in our next class meeting. Standard deviation is the amount of spread between the numbers. So if I give you all this final exam and you all get 90s to 100, that's a small deviation. Everybody got an A, which would be awesome. But if somebody got a 2%, someone else got 102%, that's a huge spread of data. So standard deviation measures the spread of data, and it's all formed around averages. So here's our little formula, okay? Looks kind of scary, but let's look inside. Let's go all the way in here. X bar is the mean. X is each number in here. So I'm taking each one of these and subtracting the mean, taking the absolute value and squaring it. We'll show you what that actually means here. And adding them up, dividing by the number of numbers, and then square rooting it. Sounds like a lot, but let's look at what we're doing first. We're adding all of these numbers. Instead of writing it out, let me just tell you, we're adding those numbers together. 1, 2, 3, 4, 5. Okay. 1 plus 2 plus 3 plus 4 plus 5. So I get 15. 1, 2, 3, 4, 5, 15 divided by 5. So the mean is 15 divided by 5, which is 3. Add them up. Sorry, I'm going to put a capital there. Add them up to 15, divide by 5, and get 3. That is what you just did over here for mean and median, and right? That's the same thing for mean. So you start with that. Now, what I want to do is I want to take each one of these numbers, x, and subtract 3, and then square it. So I'm going to take 1 minus 3, and then square that. I'm going to take 2 minus 3, square that. I'm going to take 3 minus 3, square that. 4 minus 3, 5 minus 3. And then square it. So each one of these gets squared. Now the reason we square it is to get rid of the negatives. So that everything comes out positives. 1 minus 3. Now be careful in your calculator. It depends on your calculator. Just know that every time I square something, it's going to be positive. Let's see what happens in my calculator. It may or may not do what I want it to do. 1 minus 3 is -2. If I square it, I get 4. Okay, that is what I want. Okay, I want it to be 4, even though some calculators might say -4. There's a reason with the order of operations that it might do that. Just know that once I square it, it should all be positive. 2 minus 3 is -1. -1 times -1 is +1, right? 3 minus 3, very simple. 0. 4 minus 3, guess what? That's 1. 1 squared is still 1. 5 minus 3 is 2. 2 squared is still 4. So what I've just done is in these brackets here, I just took each number minus the mean and squared it. Now I'm going to add them up. 4 plus 1 is 5, plus 0 is 5, and another 5 is 10. This symbol here tells me to add all those up. So now I've got 10. I want to divide it by n. N was 5, the number of numbers that I had. That simply gives me 2. So I like to summarize every step and make sure I didn't miss anything. So the mean was 3. I took the mean, I took each number minus the mean. By the way, you could do it the other way. Wouldn't matter because when you square it, you still will get, like in my example, 41014. Added them up. I got 10 divided by 5 is 2. So the standard deviation then is the square root of all of that. I'm going to write it out like this, which is about 1.414. You could say 1.4. Just do that in your calculator. Don't forget to do that last step. There's a lot more to this. There are cases where we do something different in the denominator. There's the definition of the term called variance before we do square root. This is what I want you to know how to do. Okay? And that completes our review. So good luck. Thank you.